I welcome you all for the fourth lecture on Fourier series and transforms. Today we will discuss following three topics: Fourier cosine transform, Fourier sine transforms, and their properties. An integral transform is a transformation in the form of an integral that produces from given functions some other new functions which depend on a different variable. As a Laplace transform, we have a function of f of t. We integrate that function, multiply by exponential, then we get a new function which is a function of variable s. So something like this we have in Fourier cosine and sine transforms. It has applications in solving ordinary differential equations, partial differential equations, and other integral equations. In lecture 3, we discussed Fourier integrals, and for an even function, we have Fourier cosine integral. So Fourier cosine transform, we will derive this from the Fourier cosine integral. So let f of x be an even function, then the Fourier integral is Fourier cosine integral, and it can be represented by equation of 1. F of x is equal to integration 0 to infinity aw cos of wx dx, where aw is given by 2 upon pi 0 to infinity f of v cos of wv dv. So while finding this Fourier cosine transform, we just rewrite this Fourier cosine integral. So we start with the coefficient aw. We write 2 pi as product of square root of 2 pi. Keep the integral as it is. Now see the first expression, root 2 upon pi bracket root 2 upon pi integration from 0 to infinity f of v cos of wv dv. Now this expression inside this bracket, this is our new function. If we see here, we are integrating with respect to variable v, and then we are putting the limits 0 and infinity. So whether we integrate with respect to variable v or with respect to variable x, it hardly make any difference. So what we are doing, replacing v by x in the expression inside this bracket, and finally we have this next expression which I have underlined red. So this function, this is our new function, we call it f cap c, and this is function of variable w. So this f cap c is the Fourier cosine transform of the function f of x, and we have equation number 2. So now aw can be written as square root 2 upon pi f cap cw. Now we use this one, and we can rewrite Fourier integral, that is Fourier cosine integral, given by 1, and finally we have equation number 3 at the last, that f of x is root 2 upon pi 0 to infinity f cap cw cos of wx dw. So I am just rewriting equation number 2, that is the Fourier cosine transform of the given function f of x. And using this Fourier cosine transform, we can rewrite the Fourier cosine integral from the equation number 1. So f of x can be written as square root 2 upon pi 0 to infinity, and the Fourier cosine integral, that is f cap c w, and this we call as equation number 3. Now very important here, that in 2 and 3 there are two variables, one is w and second one is x. While finding Fourier cosine integral, we are integrating given function f of x, we multiply this by wx, and then we are integrating with respect to x. We put the limits 0 to infinity, and after integration we have a function of w. In equation number 3, again we have two variables w and x. We are integrating with respect to w. Substitute the limits 0 and infinity, and we have a function of x. These are some basic notations. Fourier cosine transform, or you can simply say that capital F is also used. So this f cap c, this is called the Fourier cosine transform of f of x, and f of x is called the inverse Fourier cosine transform of f cap c w. Now for a given odd function, we can find out its Fourier sine integral. So we use this concept and we find Fourier sine transform. Let f of x be an odd function, then its Fourier sine integral is given by equation number 4. F of x is equal to integration 0 to infinity bw sine of wx dw, and bw is 2 upon pi 0 to infinity f of v sine of wv dv. As discussed for Fourier cosine integral, we just rewrite this coefficient bw, write 2 pi as product of square root of 2 pi, again repeat this number, and the integral 0 to infinity f of x sine wx dx. Here again I am replacing variable v by x. You can see the underlined expression here. And finally bw is square root 2 upon pi f cap subscript s and function of w. So this new function f cap sw defined by phi, equation number 5, this is the Fourier sine integral of given function f of x. Now using equation number 5, we can rewrite Fourier sine integral given by equation number 4 as f of x is equal to square root 2 upon pi integration 0 to infinity f cap s w sine of wx dw, that is equation number 6. So this f cap sw, this is called the Fourier sine transform of f of x, and f of x is called the inverse Fourier sine transform of f cap s w. There are a lot of notations for Fourier cosine transforms and Fourier sine transforms. Small f cap cw, or we can simply write down capital F with subscript c and your function small f. C I am using for cosine transform. Similarly, you can write down capital F with subscript s and your function small f. Now consider example for Fourier cosine and sine transform. For a given function f of x, which is defined from 0 to infinity, we can find out its Fourier cosine as well as Fourier sine transform. These numerical problems are very easy. You just have to use the formula and evaluate the integral. So start with Fourier cosine transform. Its formula is given by 1, that is f cap cw is square root 2 upon pi 0 to infinity f of x cos of wx dx. Now substitute the value of the function. Function is k, which is some constant defined from 0 to a, and it is 0 if x is greater than a. So this integral from 0 to infinity will be 0 to a. Put the value of the function, that is k cos of wx dx. Integrate this, you have the value, and this is the final expression for the Fourier cosine transform given in the box. Similarly, you can find out the Fourier sine transform. Put the value of the function. You can see the formula, second last line on the slide. Now the integral will be from 0 to a only. Function is k sine of wx dx integrated. Now the last expression in the box is the Fourier sine transform of given function f of x. Try this numerical problem. Find the Fourier cosine transform of e raised to power minus x. Its solution is with u square root 2 upon pi 1 upon 1 plus w square. Now we will discuss some important properties of Fourier transforms, cosine and sine transform. First one is linearity property, that Fourier cosine and sine transform, these are linear operators. So first one is f and g are two functions. Then Fourier cosine transform of a times f of x plus b times g of x is equal to a times Fourier cosine transform of f plus b times Fourier cosine transform of g. And we have the same property for Fourier sine transform. So I am proving the first one. Second part will be on the same lines. So by definition, Fourier cosine transform of f of x is given by first expression, that is square root 2 upon pi 0 to infinity f of x cos of wx dx. And similarly, we can define Fourier cosine transform of gx. Now to prove the first property, I will start with the left hand side, that Fourier cosine transform of a times f of x plus b times g of x is equal to square root 2 upon pi integration 0 to infinity. Put the value of the function, that is a times f of x plus b times g of x cos of wx. Now this integral is a linear operator, so you can separate it. A and b are constants, so you can take a and b common and see the second last line, the underlined two expressions. They are Fourier cosine transforms of f and Fourier cosine transform of g. So finally we have the result, that Fourier cosine transform of a times f plus b times g, this is equal to a times Fourier cosine transform of f plus b times Fourier cosine transform of g. Now cosine and sine transforms of derivatives. Let f of x be continuous and absolutely integrable on the x-axis. Let f dash x, first order derivative of a function f of x, be piecewise continuous on every finite interval, and let f of x tends to 0 as x tends to infinity. Then the Fourier cosine transform of f dash x is equal to w times Fourier sine transform of f of x minus root 2 upon pi f of 0. Then second one, Fourier sine transform of f dash x, this is equal to minus w times Fourier cosine transform of f of x. The proof is very easy. We just apply the definition, integrate it, and we get the result. Now proof of first part A, Fourier cosine transform of f dash x. We put the value of function f dash x in the formula, that is root 2 upon pi 0 to infinity, and now our function is f dash x cos of wx dx. Now we integrate it. We treat cos as first function and f dash x as second function and integrate it by parts. We have this expression. Now in this first expression on right side, we put the limits. When we put lower limit, that is 0, cos 0 is 1, and we get just f of 0. Upper limit, I am keeping it as it is, that limit x tends to infinity, cos of wx f of x. Now we integrate the second part, that is 0 to infinity f of x minus w times sine of wx dx. We just rewrite it, and finally we have this expression. I have underlined this. Now coming to this limit part, limit x tends to infinity. When x tends to infinity, cos of wx, it is going to be something finite, right? But it is given that f of x tends to 0 as x tends to infinity, right? So 0 into something finite is 0. So this limit part is also 0. And we just have the second expression, minus f of 0 multiplied by square root of 2 upon pi. And if you see the underlined expression in the second line, it is nothing but it is the Fourier sine transform of the function f of x, and hence we have the result for Fourier cosine transform of f dash x. Similarly, we can prove the second part, that Fourier sine transform of f dash x. Put the value of function in the Fourier sine transform. Assign sine as the first function, and our second function is f dash x. Integrate this by part. Now the first expression, that is sine wx f of x, it is 0 for the lower limit as well as for the upper limit. And we just have the second expression in the form of integral 0 to infinity f of x cos of wx, and w we have dx. Take w common, and if you see this expression, this is the Fourier cosine transform of f of x. So finally we have Fourier cosine transform of first order derivative. It is in terms of Fourier sine transform of your function f, and Fourier sine transform of f dash is in the form of Fourier cosine transform of function f of x. These proofs are very important. Now one more result. This is related to the previous one, cosine and sine transform of derivatives. So using that result, find the Fourier cosine transform of second order derivative of function f and Fourier sine transform of second order derivative. So I'm starting with Fourier cosine transform of f double dash. You can solve this problem directly also. Apply the formula and just integrate that expression twice. We can get the result. But I am proving this result using the property of the derivatives. So Fourier cosine transform of f double dash x is, I can rewrite the second order derivative, right? Fourier cosine transform of f dash x, and then it's again first order derivative. Now in this expression, we use the property that Fourier cosine transform of f dash x is w times Fourier sine transform of the function f minus root 2 upon pi f of 0. So in this expression A, that is the property of the Fourier cosine and sine transform of first order derivative. In this expression, which I have written on the right hand side, replace your function f of x by f double dash. We apply this property and we have, it is w times Fourier sine transform of f dash x minus root 2 upon pi f dash 0. Now in this expression, I am saying use now B. We have Fourier sine transform of f dash x. This is the first order derivative and we want to find out it Fourier sine transform. So now again we use here property B, put the value, simplify this. We have equation number 7, that is the Fourier cosine transform of second order derivative is given by this expression. Now to find out the Fourier sine transform of f double dash x, we write this second order derivative as f dash x and then again its first order derivative. Now we use property B, I have written above. Then its solution will be in the form of Fourier cosine transform of f dash x. Now again we can use the property A, that is Fourier cosine transform of f dash x. Simplify this, we have finally expression given by equation number 8, that Fourier sine transform of f double dash x. So just now we discussed the property of Fourier cosine and sine transforms of second order derivative. So along with that proof, one may ask some additional question. For example, using that property of second order derivatives, cosine and sine transform, find the Fourier cosine transform of e raised to power minus ax, where a is greater than 0. You can easily find out the Fourier cosine transform of e raised to power minus ax directly by using the formula. It's very easy. But here I am solving this problem using this property. So let f of x be e raised to power minus ax. Its first order derivative is minus a times e raised to power minus ax. Second order derivative is a squared e raised to power minus ax. Now recall result number 7, that Fourier cosine transform of second order derivative f double dash x is equal to minus w square Fourier cosine transform of f of x minus root 2 upon pi f dash 0. Now put all the values f of x, f double dash x and f dash 0 in this formula. Now use a property that you can take on the left hand side you can take a square common. So it is just a square Fourier cosine transform of e raised to power minus ax. Put the values and simplify on the right hand side. Now see the left side and the right side. We have the same expression, Fourier cosine transform of e raised to power minus ax. Combine these two function terms, simplify, and finally we have Fourier cosine transform of e raised to power minus ax. Generally, this problem comes as a part of that proof, Fourier cosine and sine transforms of derivative. Otherwise, you can solve it directly also. Try these numerical problems for Fourier cosine transforms and Fourier sine transforms of given functions. You have to use the formula and just evaluate the integrals.